So now let's say you got a surface. You've constructed your surface and you're trying to determine how much electric field is going into it. How do you decide that?
Second one.
Use Gauss's law.
All right, so let's say that you're trying to check these spheres out, right? You're like, okay, I have some amount of x, some amount of y, right? Some amount of
It's
z.
just going to camera. Stop moving it. I want to see the words.
Oh, sorry. What am I talking? All right, so we have a volume. My bad. Oh my god. So how do you check what is inside of it? You integrate over the space, right? So you integrate with respect to x, you integrate with respect to y, and then you integrate with respect to z. In the same way, you integrate your sphere and your cylinders, right? And now something interesting. There was some really brilliant vector calculus that was devised like years ago, where some people found out that if you were to take any closed surface, then the total divergence inside of the surface. Oh, great! That's what we're trying to find, right? We have a divergence that we're trying to find that's integrated over. So they found that this is equal to the surface, which encloses your field, right? So the reason why we put this like in the middle of the ellipse, is because the surface is closed. We're indicating that that there can be a volume inside of it.
Yeah.
I have to clear off the table.
That's okay.
Wait. Oh, so you can't see it.
We're gonna have so much footage of us in second year.
Just because we streamed so many hours of it.
Oh, that looks much better.
That looks almost legible. Can you check your phone?
Can
When
you
we're all older.
turn down the brightness of the TV? That might
Oh, yeah, sure, why not?
be able to see
I'm not
it
sure
better.
how to.
Yeah, it's
There should be a
legible.
remote
Send the
somewhere.
link.
Oh, I can change my paper to a slightly lighter shade. So a slightly darker shade.
That would.
Yeah, like an orangey.
No, iPad.
Because like if you look at it, or it might just be that the lighting's not great here.
That is. Wait.
Is that good? Better? iPad is amazing. I agree. iPads are
It's legible. You can see it. Yeah.
Can you turn in or can you check the volume? Jesse, speak.
Hello?
Yeah, that's fine. Okay.
Should we get the desk lamp?
Should we get the link?
Should we use the desk lamp?
Because I feel like if you use the lamp at Jesse, it'll have less contrast. Or am I just like crazy?
We want there to be as little contrast as
Oh, that's
possible.
As much contrast?
Or between Jesse and the thing.
How is this possible?
As well possible.
Not this.
Why are you doing camera? Oh, because you need your papers.
I got.
Okay.
But like, how is this possible?
Wait, so
Like,
we made.
Actually, Nat, turn the desk light off.
Like, how do I only have one picture?
It doesn't really make a difference.
Should we turn these lights off? We could try turning lights off and might make it more.
Yeah, let's turn lights
Try
off.
leaving the LEDs on and like. Oh, that's much better. I think for me, because I just couldn't see what's going on before.
If it's better for you though, then we'll
No, I think it was just in the moment.
Well, it's much better for me. I don't know about everyone else.
Okay.
You
as
can
long
keep
as-
them off if it's better for future.
Check
Yeah,
them.
okay, I don't
Check
understand
those,
things
right?
even when I see them, so it's like. So if we make our summary sheets, basically, do we have to make two versions? One where we have like definitions and shit on them, and one where we don't, in case we bring one with like definitions and he flips his shit? Like.
He's gonna flip shit either way.
Oh
Yeah,
yeah, he's definitely.
I
He's just
honestly,
like that.
I'm just gonna ignore what he says and.
Do what you want?
Yeah.
Okay, I just don't want it to get taken away from me because I'm so fucked up. I don't have much to
Realistically,
use.
how much is that gonna help me on the exam?
I mean, at least if you can write an equation down, you'll get 1.70.
Yeah,
so,
but
so
it's,
yeah, that's something to
but
talk
like,
about.
I'm sorry.
my point is that like, if 70% of the class failed with a 2-page front and back
Can you
unrestricted
use a
cheat
darker
sheet,
color
what's the problem of including one example
and
on
slightly
our
thicker?
1-page cheat
Alright.
sheet
I just want to see if
for
it helps.
our final?
Yeah.
He's screwing himself
Like,
over
I know.
because it's making
Darker
it look
color
worse
for the-
for him.
I know, and I'm like, if you wanted us to have a formula sheet, you could have provided it to us.
Yeah,
Because a
that's-
formula sheet and a cheat sheet are two very different
You
things.
could
That's
have
better.
fought us.
That's
I don't
better.
know.
Thank you,
That's-
Jessica.
Yeah,
That's a good
we
point.
can color up, like.
I'm
No,
not
no,
sure
okay,
that's
no.
order.
Him teaching back up there, that's, you're asking too much.
You're asking too much.
That's the key.
Um,
Yeah, I thought you meeting them.
No, I literally, like, when I took my
So
nap
much
today, I
trouble
like had a dream
Actually.
that, like, I was so frustrated during the EMAG finals that I just got up and read my paper. Like, I just started screaming. But what would happen if you just did that? What if you just got up in the middle of your exam, started screaming and laughed?
I would scream with whoever's doing that.
Like, would that cause anarchy? Would other people join in?
I would join in. I would join in.
Yeah,
For sure.
I just,
Yeah.
I feel like if you failed the course and took the supplemental exam,
yeah.
I feel like the supplemental would be a lot easier than whatever he's going to give us. Plus, it gives you more time to
I'll be
study.
honest, I don't think, okay. How do I phrase this? I don't think this exam is going to be that bad. Like, I think the problem is going to be understanding any of it.
I think the other issue though
Because
is
the
that-
midterm
It wasn't.
would have been a perfectly fair, perfectly fine
If we
midterm.
understood
No,
what
the
the
Yeah.
course was.
midterm was fine, but like none of us understood anything.
It didn't mean
Yeah.
anything to us.
Yeah.
Like, I could tell looking at the questions if I knew the material, it would have been no
Yeah,
problem.
Yeah, no, it was very fair.
It
It was like,
seven
it
people
was
who
very
got-
fair.
Those 7 people who got 100%, only reason they got 100% is because they killed themselves trying to learn all this stuff.
I
Or
did
they
not
were.
kill myself trying to learn this stuff, and please, I will make sure that you guys actually understand this shit, so you won't be complaining.
Did you get 95
Focus.
to 100 on the
I got
midterm?
92 because I made a stupid calculation mistake.
So you're one of the people that brought up the average 10%.
Shush. I'm trying to teach you guys, please. Please.
That's the only reason this isn't a mom. Also, you fed us, so there's that.
Yes.
Guys,
Just
can we
chill.
continue?
Just chill. Alright, so we kind of do you kind of understand, right, why we have crow and what crow and divergence represent? Why those are the only two kind of descriptions for how vectors move in space, right? Do you kind of understand that any combination of crow and divergence, just like any combination of infinite cosine and sine curves, right, will make up any function, in that these will make up all fields that will ever exist? Like some component of the two, maybe some more over some areas and some, maybe more crow in one area and more divergence in the other. Kind of understand?
It makes sense in the context of vectors and math, but I'm still like kind of
Okay,
lost in how it
okay,
relates to,
alright.
like specifically the fields, because I know like in general vectors are supposed to model those fields, but like I guess it's
Yeah,
questionable
sure.
things.
So
Alright, Jesse,
yeah.
go ahead, I'll ask my question after.
So do you also kind of understand why we pay attention to the so-called identities of the of these concepts, right? The identity is usually like, for instance, like 0 plus anything is equal to anything, right? So these are identities, like the things that don't change, like the operations, like the specific value of operations that you can apply that doesn't change your result from the initial thing, right? So the identity of this of this field, right? If you were to superimpose another field on it, what fields can you superimpose that wouldn't cause the curl or the divergence to change? So you understand that if you impose nothing at all, right, which is the field on the right, that's fine. If you impose a field that's entirely of uniform lines, that's also fine, right? And you also understand that because we're trying to find a divergence, right, we pick a point, we're like, let's figure out a more general method to figure out like if there's any divergence in any area. So then we decided that there is one sensible unit like volume to use per coordinate system that would be easy to calculate. If you were to put a knight-shaped piece in there in the uniform field, it will still have a divergence of 0 out of itself. But trying to model that like knight piece as mathematical quantity is just very difficult. So you would much rather include the empty field around the knights, right? And then put in maybe a box, right? So you draw a big box like outside of the knight, and you're like, let me model the surface of the knight in terms of my surface, right? And I grow the surface from one point. And then after you finish your calculation, you take a derivative of your x, of a z, of a y, and then you shrink by, and what that does is you shrink your shape into like infinite small, right? So you just make a point, right? So a point is modeled by, your sphere, right? You also understand that if you were to like take a cylinder, right, and then like stretch it out infinite like radius, you get a plane, right? Like you just have radius is 0. Radius is like infinite. What else do you know? You know that if you were, let's say, trying to model like a double plate capacitor, right? Like what would you do? Like similar to this case, right? Instead of using two surfaces like that's exactly opposite to each other, you're just like, I'm just gonna imagine my parallel capacitor is just like a box, and then my box will have like some sides that don't matter so much, right? Because let's say these are my capacitors. You understand that the like space in the middle is just void, like
air.
but you can still like, yeah, this is like, let's say it's air, right? So but you can still model this as a box, right? Because that's easy for you, because the field from the other side, because it's air, there's nothing, right? So this is the general idea of how to use Gaussian surfaces. Do you kind of understand that? Right.
Yeah.
So
A point is modeled by a sphere, a plane is modeled by a cube, and I'm assuming line is modeled by a cylinder.
line is modeled by a cylinder. Yeah, good point. So
Because
line is modeled by a
it's symmetrical
cylinder
in that
where
way.
the,
Okay, that actually makes
Because it's
sense.
radial, right?
That makes sense.
That explains so much. That's what he's been going on
So-
about.
Yeah, so please just shut up and listen. All right.
Sorry.
So
Okay, so
Point
I'm sorry.
is measured by a sphere.
yeah.
It's because it's a radial field that matches the sphere.
Plane is
And the
measured by
reason that Gaussian shapes always have to be closed is
Jesse,
so we can model them better, like.
is yeah. So
how much so I can still sleep?
Hmm?
How much so I can still sleep?
so you can still see at which time.
12.
12.
Or
I would take 15.
15?
What is that? Oh,
17.
okay.
15 milligrams is like half a cup of coffee or less. So yeah, so the point is just like, if I don't say dx, which is just jargon, I will just say that limit x equal to 0, right? Which is the same as like dx, but you understand that's the same?
It's
Alright, cool.
1, 2, 3.
Why does it
Mr.
do
Wi-Fi, I think. Or 180 something.
So now let's say we're trying to observe divergence. Let's say now we're trying to devise something for curl, right? How do we tell if something is curly? Go for it.
I have no idea, but I do have a question.
Go for it.
So for curl, I still don't quite understand what the difference between curl and divergence are. Divergence sits in a circle and curl is just outwards. Is that it?
Yeah, so
So-
this is only divergence, right?
Yeah.
The divergence one is just going outward, exactly what you think it means. And curl just is exactly what you think it means. It just curls back on itself.
And other than like him giving us
Oh! Sorry, I
No,
just
no,
had a
okay.
revelation. Okay.
It's fine. Go for it.
other than him basically giving us the model of what the field's supposed to look like, we wouldn't actually know. Oh wait, so in certain cases with the field's curl and divergence are supposed to equal 0, right?
Yes. In
Okay,
this
so
case,
I
equals
like
0.
right now.
And this
Don't
case-
think too much. Just like listen and then
Okay.
like absorb it at the end of.
There are equations for determining curl and divergence.
Yeah.
If you
So-
put them in the appropriate coordinate system, which is
Yes.
why you can only use these compliant spheres, right?
Yeah,
And
there
other
are.
You can only use compliant
Sorry?
shapes, otherwise you'll find yourself in the calculation black hole.
So is like the fact that they're closed only for calculations still?
That they're closed? You're okay, so
The
look,
Gaussian
here.
surfaces.
Yeah.
So
Yeah.
fields extend infinitely.
Yeah. That makes
Gaussian surfaces we're only measuring in.
Shush.
Sorry.
No, just come look here. Just come look here, okay? So if I were to put a sphere, right, around our circle, and now our circle has like lines going into and out of it, right? Our sphere. So let's say that I'm not gonna put my closed surface. I'm gonna like punch a hole in my eggshell, right? So I'm gonna do like over here. I'm just gonna be like, okay, this part of the surface I'm not gonna be measuring, right? This is my open surface. My open surface just means that it's not closed, right? So you understand that what will happen is you will miss part of the field going into it, but you will have calculated the part of the field that's going out of it on the other side, right? So now your total isn't 0.
So really it's just like basically
You
us imagining
only
shapes
closed
and
shapes are
okay.
compliant to our
Okay.
method of measurement, right?
Okay.
Like otherwise the two just doesn't break. It just doesn't work. It just breaks.
I mean, in this case, you could also have enough curl that it just enters and exits, couldn't you?
You can try to like dig out shapes that will work, right? But like that's also more mathematically complicated to model, and also they will just be a subset of these with some topological like morphing applied. Like you can mathematically apply a morph after you have determined your like base shape, right? Like just not think so hard so far, okay? So all right, what do we think is a sensible way to determine if a field has some curl? Like what would be the first thing you think of, right? What if I was just to stand somewhere in the field and let the current push me? I'm a bolt, right? I float and see if I go back to the same point. Does that mean that the field curls?
Yes.
Okay, cool, right? So now I have to generalize this to 3 dimensions, right? I'm not on a 2D like Earth's surface. Now I can fly in fucking space. So now what do? Like, I can follow every single point, but like that takes forever, right? Because our field is infinitely large. So what if I want to find out that if like, can I maybe figure out a way to reduce the dimensions I'm dealing with, right? Maybe instead of dealing with like a whole space, I'm dealing with only a plane. So what about I just take like a circle, right? And I arbitrarily run it along like an infinitely long cylinder side in the space. So now every single field, which will have some sort of component like going like a roller coaster this way, right? Like a twisted butterfly. Can you imagine that? With your hair tie. So the field is like that, right? So I'm drawing a circle somewhere through it. So you understand that at some point, when my circle crosses the specific 4 points of contact that it has with the roller coaster, right? With the field lines, it will have 2 that will be pointing downward. It will have 2 that will be pointing downward and 2 that will be pointing upward, right? But all of them will be going like clockwise or counterclockwise, all of them, right? So if all your fields at all points when you run a circle through it, right, are all going in the same like counterclockwise or clockwise direction, which how do you measure that, right? You just measure that some are going out of it, some are going down, some are pushing the loop up, right? So if you just imagine that all of these vectors are pushing your loop, let's say 2 pushes up, 2 pushes down, then you've effectively determined that this entire cylinder of space doesn't have any only has some curl in it, right? So the way to represent this mathematically would be to say that, like, if we're mathematicians, we're smart. We're gonna pick 2 points of the loop. We're gonna like divide our loop into 2 segments, such that one side will have A amount of field lines going into it, and B will have those amounts exiting it. And therefore, hey, our sum is also 0. So this is an ampere loop. And can anyone guess what kind of ampere loops might exist, might be valid, might be compliant to our coordinate systems? Like, what's the 2D versions of a cube? You know this.
Square.
There you go. Awesome.
Wait,
All right.
so are there only 2? Square and circle?
Yeah, well, rectangle and ellipse, but yeah. Yeah, rectangle and ellipse. Right, so 2D version of a sphere, right? Cylinder is a hybrid of the 2, so we don't count extra for that, right? So valid ampere loops, only 2 of them. Cool? Got this?
Sorry, what
Alright.
do you use ampere loops for?
All right, well, this is for determining if the field, okay, so if field has divergence, and the way that you would do this, right? So we're gonna have 2 tools in our toolbox, right? We're gonna have this test called the ampere loop test, where step 1 is you draw a loop, draw a compliant loop. Where step 2 is that you're going to divide into. Okay, well actually, the smarter way is to sometimes that you can use, sometimes doesn't work. Divide into 2 parts, right, or 2 groups of segments. So similarly to how the Google logo is divided, I might divide it up into like this part and the gray part, right? So in this example, it is purple and gray. And then if filled lines going into one equals dot out of another, then total, sorry, a task for curl, my bad. What the fuck am I talking about? All right, then the total curl is 0.
Can you draw the field?
What field?
If there is a field, like, can you make a test case?
Oh, I see. So
Like an example.
Oh, sure, yeah, later. Go for it.
yeah,
Yeah, okay, so let's say that we have a capacitor, right? We have a double plate capacitor. And you have a wire connected to the plate and then another wire connected to the other side of the plate, right? So how do you wanna, let's say that I wanna figure out that if let's say there's any field that is curling, right? So I'm gonna draw a ampere loop which kind of goes that way, let's say. But maybe that's too small, right? Like, so this is very hard to draw, but this is on the YZ plane, okay? And then this capacitor is centered at 0, 0. Like, this point is 0 origin, right? So I'm trying to draw a vertical line. I'm trying to draw a vertical loop.
Okay.
So you understand that this would be an effective way to see if all of the field lines, right? We're talking about general field lines because you didn't let me finish yet talking about what these can actually be used for. But if the general field lines going into your thing, right, equals all the current that's flowing outside of your thing, right? Which, by the way, you should remember that currents flow from the positive end of the battery, which is the longer side, to the negative end of the battery, which is the shorter side. So it would have like a current flow this way, right? And this would be the negative, and you would apply some sort of voltage to this, right? So this would be one example. but let me finish a little bit first. So these are the Maxwell's equations. So now can you sort of guess what they mean, right? This is very simple. Like we have what the divergence of B, right? So I'll just write what these things are, right? So D is the electric field
The divergence is
density.
zero because the magnetic fields go in circles.
Yeah. And if you have circles, it doesn't go
Oh,
up.
flux density, yeah.
And if it's like, I just.
Check it. Flux density. And then E is a composite of D, which is dependent upon epsilon, which is a just. So basically in physics, whenever people figure out that things are proportional to each other, they're just like, okay, we're gonna make an equation and then define an arbitrary thing, and then we're gonna specify that this is specific to the material. And because that's always the case, see? Whatever we can blame material choice. Cool. So this is literally just a proportionality constant. That because it's specific to the material and the basic simple material is vacuum, then we're just like, okay, well, we're gonna say that each material's specific proportionality constant is actually proportional to the proportion to the such quantity for vacuum. Great. So now we're just gonna put another proportionality constant in front of it, and we're gonna call epsilon 0 the one for vacuum.
Nice.
All right. So what this is the electric field intensity. Similarly, the B is the magnetic field density, and the oh, sorry, that's my bad. 1 second. Okay, so similarly, we have a magnetic field density, which I'm just gonna write as like phi, because that's what's correct. This one can also be, instead of called like D, can also be called just phi. So you understand that's equal to that, right? D is equal to that. So, oh, sorry, my bad. This is backwards. 1 second, I'm sorry, I'm teaching wrong things. Shit.
Sorry, Jesse.
Yes.
So, D is electric flux, right? Is electric flux different from electric flux density?
she's correcting.
Oh, okay.
This is electric flux in total, right? Total. My bad. So what would happen is that the total is like that you will be able to integrate your electric flux density with respect to your volume, and then you get your electric flux back, okay? So that's what it means to be totaling up.
Okay.
So similarly, magnetic flux, right? Magnetic flux exists, and then your magnetic field. It died.
Oh.
I'm upset. Okay, my back should be over
I
there.
have a fat charger.
Here,
Like a really fast
you can use
charger.
Simmer's computer charger.
Oh, use your computer charger. Computer chargers are really bad.
Yeah, I have one in my back.
That's okay,
I
just
don't
use
think
this
it's
one.
back here. Is it there?
Shit. I'm so sorry.
All good, Jesse. Don't even
It's all
worry.
good. I understand so much more now. Like legit.
Cool, good. Oh right, I forgot. I thought we were gonna have to take a break just because
No,
of
it's
this
okay.
change.
Don't even worry. It's like 5 minutes.
Oh my god, it's instantaneous. I
You
love
just need
that.
to wait for your.
Eat your cake, girl.
Yeah.
Thank you.
Generally, Jesse, this 20 minutes has been more helpful.
Yeah.
Than
Yeah.
anything he's
Literally
done
the
ever
entire
said.
class. Like seriously, it's amazing.
Oh. Only because I just haven't seen that much last.
Okay, since we're kind of pausing for a second, I just want to take a moment and point out when I looked over there, you two were in the exact same pose with the exact same expression of slight
I thought she was
confusion.
asleep in some numbers like this.
No, you were literally there just like,
Like I swear, I
I'm sorry, paying attention, Jesse.
no,
I'm just
You guys look like twins. Like literally your entire your facial expressions are exactly.
Oh, I think
the
my pens are connected. They're shut off. Have to figure out how to connect it.
Just put it back on
Just
the.
put it.
Oh, it's connected.
Yeah.
Nice, cool.
Charge it.
So this is magnetic flux, and then magnetic flux density is. Well, I have a beautiful palette. Oh my god, it's awesome. iPad is awesome.
So remind me the flux versus the field again.
Yeah.
Flux is number of field lines going through the surface.
Okay, right.
Yeah, and then you can use flux to get field through gas as well. I think.
Yeah.
And then flux density is like
Point
per.
line and then plane thing.
I know.
Wait, so field density.
Alright, later. I will explain.
Okay.
So magnetic flux, right? This is also the total magnetic flux. It's calculated by the magnetic flux density, right? And then the flux density you see is just something. So the flux density, right, is like all your flux going like is the measure of density going through anything. So like if it goes through cardboard, same density, right? If it goes through metal, density, right? But also, you notice that electric flux, the true flux that's generated by your electronic device, is gonna be constant underlying, right? Like let's say that you're passing current through the air like thunder, right? When thunder passes through, it passing through different material will cause it to move faster or slower. But then like the underlying voltage that it has is still the same. So in order to actually work with this experimentally versus theoretically, we're correcting for the material. Does that make any sense?
Mhm.
Like,
And that's
So-
what the lesser E is.
yeah, because like you can measure D, right, in any sort of material. You can measure this in the flat metal cylinder. But then how do you get the field intensity? Because if you use the copper cylinder, some other experimentalist use like steel cylinder, you'll get different results, right? So you correct it by this and then report your E. That's what you would do, right? So similarly, we have the ones for magnetic field. So you get H as your magnetic field intensity, right? And then you get another proportionality constant to the material, right? Just because we want to correct for material and we don't know what to use, so we invent a constant. And then we're like, okay, well, we can also measure that with relative to vacuum. So what is this actually called, right? This is called electric. Like what would you name this, right? Like, wouldn't this be a name that you would pick? You know, this is electric field permittivity. Right? Wouldn't this be a name that you want to pick for what you're trying to describe, right? And this is magnetic field. Well, we don't want to use the same word, so we're going to use something different. We're going to call it susceptibility. Such vague words, but English is beautiful in that it has many things that allow you to turn your words into different forms. So we turned our word into a noun. That's cool. All right, so okay, I'm high right now. Sorry for that. Go for it.
Just something that's bothering me.
Yeah.
You forgot to change electric to
To
magnetic.
magnetic for the second
Oh,
example.
my bad. All right.
I know that's gonna cause confusion when you post
All
these.
right. All right. Let's do that.
Copy and paste.
Yeah.
Yes. iPad powers.
iPad powers, 100%. All right, good? We're good?
It's a tiny magnetic.
Shush. It's brilliant that I'm able to do and talk at all, okay? So, just shush. Up there, what does this mean, right? We already understood what a field without divergence means. So it's saying that the B, what does B mean? Magnetic field intensity is without divergence. Is that what it's saying?
Yes.
Right? Okay. So what does it mean, right? It's saying that any sort of magnetic field will go in like circles like this, right? It will have only curl. So all the magnetic fields, they will curl back into something.
So magnetic fields, like they go round.
They go round and round like a horse on the carousel. Alright, so
Definitely gonna remember this. That's all it's gonna be in my mind.
okay.
Sorry. It's a good thing though, Jesse.
Yeah, it's good. It's a good
Alright, so divergence is 0. So what causes divergence, right? You see how the electric field is measured, right? Is if I were to put a positive test charge in my space and then I follow its trajectory over the next second, if it goes left, I'm like magnetic electric field left, right? So this is hard.
Jesse, do you need a minute to laugh?
Yeah, let it out.
Yeah, let it out.
Okay.
Jesse.
Thank you. This is actually so funny. Okay, so
Sorry.
Jesse, do you need to like shake the giggles out?
Shake the giggles
Come
out.
on, we're gonna shake the giggles out. Just like
just stop talking. I'll be fine.
Okay.
I can just breathe very deep and not have to laugh. But if I'm at that trigger,
Okay, I'll just shut up. How about?
sorry for that.
It's okay.
No, I don't mean to victimize you. Oh shit. Okay. All right. So basically, when you follow your when the field has divergence, right? When you place test charges on surfaces that are closed, let's say I place a shield over this positive charge, right, in the middle, right? If the shield is negatively charged, it will want to be attracted. So the shield will shrink and shrink and shrink and go towards your 1 point. So that's how you know your 1 point has divergence, right? How you know is that there is some non-zero amount of field going either into it or out of it, right? Because your objects are either collectively attracted to it or repelled from it. If it's just vacuum, your object's not gonna move, right? So do you understand, like, this is like a space, this is like a attack frontier it's like the war front for aliens attacking Earth, right? You understand that you want to enclose Earth to make sure that there's nothing going out of it, right? So it has like fucking spaceships over here, right? And your spaceships are going inside of your Earth to attack your population. And when they do collide, you understand that they have a target here. So basically what the electric field, the first thing is saying, right, is that the divergence of the electric field density, right, the divergence of what you measure. If you were to measure along a sphere, right, the total divergence will be some amount, and that amount is somewhat proportional to how much charge you have inside, right? And that you kind of understand, because if you were to put stronger positive charge in the middle, negative charge more attracted to it, move faster. Cool. Go for it.
I'm confused about what the shape of spaceships are in this metaphor.
Test charges.
Those are
Spaceships
test
attacking
charges?
Earth.
Those are test charges?
Yeah, test charges.
Okay, because I thought they were like electric field or something.
Yeah. So I'll just say that test charges.
That's the definition of field.
Spaceships?
No.
Test charges.
The definition of a vector field is that for every point in your supposed space, there is a vector which can correspond to it. It's a bijection of it's a function of a vector field is a function of your space, whereby it returns a vector at 1 point. Does that make sense? So test charges are your spaceships.
Jeez.
Understand? Cool. So basically, what this is saying is that the total amount of, right, like when measuring, so here's how you write your divergence, okay? Or just write the entire test procedure down so you guys don't get confused over here, okay? So this is a test for if field has divergence, right? So you first define compliant surface, right? And observe how points on surface observe points on surface. And how do you observe, right? How do you observe? You put a test charge, right? By putting a test charge and seeing where it moves. So what happens if your charge is suddenly going from motionless to moving at some speed, right? In classical, like high school physics, we learned that to Newton's first law, right? If object is if object is stationary or in or at constant velocity, then there's no force being applied to it, right? So what it means is that if your charges were to have accelerated, you've applied force to it. What applied the force to it? There's nothing in space. That's the imaginary electric field, okay? So what you would say is that we absorb, if you were a scientist back in the 1700s, you'd be like, my charge went from stationary to accelerating. That's violating what Newton says. So I must give a name to this imaginary field, which I imagine must exist, which actually does, right? So what I would say is that I'm saying that the field did work. It did my work for me, right? And work is like physical, is a proper term in physics, right? Is something in classical physics that was defined, right? Do you know what work is?
It's
Force and distance.
Right, yeah, it's related to force and distance. So how do you measure how do you measure this discrepancy from the Newton's laws, right? What kind of force is being applied? We apply proportionality constant. We're like acceleration, right? So we're like, okay, so the proportion of like if you're able to accelerate faster, if you're able to do this faster in less distance, then we're just saying that our work is equal to force per like distance, right? We're just gonna say, sorry, it's force times distance, right? So if it did more work, it either applied more force per point, or it applied that force over a longer distance, right? So I'm like, okay, great. Now I can describe what this is. But obviously, this is in a very easy to calculate form. In a slightly more difficult to calculate form, maybe the electric field did work, but it like shoved the particle all in 3D, right? How are you gonna count that? So I'm gonna take the line integral following this line, very, very easy, right? So you understand that this is your dw, right? Sorry, this is your line. Call this L, right? L is defined by a function, right? So L is defined for everywhere in space in x, y, z, right?
okay.
You understand that you can also parameterize this and write it with respect to time, right? You can define your one singular little arrow pointing tangential to your line as your dl, right? The differential length, as in it is where this line is pointing at and what its magnitude is at this very particular point. You have found the tangential thing to the like parabola, right? And it's just tangential, and then its magnitude is equal, like maybe very big here and maybe like slightly smaller here, right? So you represent it as the length of the vector. So essentially, if you were to take this differential length, it's encompassing all the information that you have about this line, right? And your dl would also be, you would integrate this over, if you were to have defined your line as within space, you would integrate your dl, right, with respect to the function that defines a line, right? So let's say dl, and let's say the line thing is like, let's say that our line, for very simple sake, right, we're gonna say that it is x. Let's just say it's only moving towards the x direction. Like literally this line is just going that way, okay? So in this case, you draw the, you write this specific notation to indicate that you're going to integrate over a line in space. Do you understand that?
But only the x direction.
Well, you're gonna
No,
put,
the x is.
you're gonna substitute x, right, with your line thing, right? So I can put any vector here, right? If I put like n, right, and then maybe like n is defined as like,
X, Y, Z.
yeah, I can,
Okay.
yeah, and then n is a function similar to here, right, where it's defined as
like
n
true
of x, y, z,
Yeah.
right? Or it can be defined as like n of t, and then this could potentially be like 3n squared, and then like x, and then y cubed, like x, right? Plus 1y minus 1z, right? This is an arbitrary thing in space. Understand? Cool.
Okay,
Mm.
do you
So-
guys follow this?
I
Okay, sorry. Okay.
Cool.
Well,
I'll get there.
I think so.
All right. So how do we write? So how do we generalize our observation of the field doing work? Right. We're gonna say it's not force over distance. It's force along the line where it moved. So we're gonna say that it's the force along the line, and we write it like that. Okay.
Sorry, Jesse.
You
That
understand?
integral there, integral of E, the electric field times MdL, what is that
Arbitrary.
what is that define?
Demonstration. Oh, that is integrating the line, right? So
Okay,
this
but what
is,
does that give you?
this gives you O. Oh, sorry. No, this. Oh, this gives you the amount of electric field along that line.
Oh, okay, that makes sense. Thank you.
All right. Should I write this?
Yeah.
Yeah.
All right. Cool. I should just be typing or something. No, but actually, it's hard to type in this thing. All right. Cool.
So that's flux.
No.
No.
We've defined work. We saw that magically somehow our test charge was being moved without me pushing it. And that defies Newton's law, and that means force was applied. And if the charge moved very far, then the amount of work we say that the field did was a lot, right? So now I'm gonna define work as just some amount of force over some sort of line, right? So now we're gonna get into what a force means, right? So a force can be, here, okay, 1 second. The force can be, okay, what force means? So what can create force? Nothing can create force. Okay, but like you have the total force at one point in space is the electric force plus the magnetic force, right? So this is called the Lorentz force law, right? So you define your electric force, right? Which is based on the definition of our test charge. We're like, okay, we're gonna say that the amount of force that we experimentally measured would be dependent upon what kind of charged particle that we use in the first place. So we want to eliminate the variability between different scientists using different particles, right? So we're like, we're going to normalize by applying a proportionality constant with respect to charge. So we say charge and electric field, right? And that reveals the underlying quantity that we're trying to measure, which is electric field. So you understand that the electric field can be influenced, right? Can be multiplied by, like when you try to measure it, by the material that you use, by the charge that you use, okay? So similarly, so now we've successfully defined force, I guess. We can talk about, right, so what's the easiest scenario that you would set up to measure, to model force, right? How do you specifically find out, like, the amount of force between two charges? Let's say that I have, like, I have the field in empty space and I put one charge inside of it, and then I have another charge that I'm measuring from, right? What would model the total amount of forces between these 2 points? So this is very classical, right? This is just Coulomb's law, which is force is equal to charge 1, charge 2, right? The amount of these, that makes a lot of sense, right? Because you would have more, because you would have like more charge if you were to, sorry, the force would be stronger if your charge was stronger. And then you would divide this over some material quantity, right? Because you want to normalize for material. And you just happen to find that your thing is like 4 pi of distance.
Oh, wait. This is.
Cool.
No, it's Coulomb's law, but it's. I was going to say it's very similar to gravitational.
It's the same,
It's
except
the same.
instead of mass, you have
mass.
charge.
Yeah.
It's identical.
Yeah, okay, that's a good
Because they're
concept.
fundamental forces.
Inverse square laws. that are fundamental.
Yeah, so this is the thing where if you were to go far enough from something, it drops orders of magnitude instead of linearly. So this is a good thing, right? Because you don't want to be pulled to the earth too strongly. I don't want to be pulled by Oscar over there. So now we've defined.
So you're getting pulled by other people.
So this is the most classical definition of force, right? How do we define this in a vector field? Because this is a scalar, right? We want to add a hat to it. We want to put a green hat over it and be like, you suck. So we're going to put just some arbitrary amount of distance vector, right? We're just going to put like some sort of random vector to multiply that to. But what kind of vector? We're going to say that it's the vector where precisely if you were to put that describes distance. Okay, so distance between 2 points. Right, so you would specifically say, I'm going to define a vector from my point 1 to point 2, right? I'm going to define a vector this way. Okay, so how do I describe this? Let's say we can use position vectors, right? Do you remember any of this? So like x1, sorry.
Yeah,
R1, R2, right? And instead of calling our points 2 and 1, we're going to call them observation and state and observation. So in the future, we can refer to the observation point as the test charge. Same thing, okay? So your observation is without anything, and the state is prime, okay? So that's how we're going to define our distance. And then to write our distance, we're going to be like, okay, we're going to put the distance is represented by the vector itself, right? So the vector of r over r prime, r minus r prime, right? And then we're gonna times that by the normal vector, which is, am I teaching this correctly?
I thought it
Yeah, 'cause
was.
it's gonna be like the absolute value of that minus that.
Absolute value of this?
Like no, like
just break
No,
down.
it was like-
something like that, right?
No, it's multiplied by the normal vector, but to get the normal vector, you have the vector over the absolute value.
The absolute value, something like
Yeah.
that. It's
Yeah.
So it's
Oh,
the
it's
vector
wrong.
vector over the absolute
Can you see
value.
the equation?
Oh. Square law, thank you. Inverse square law. Okay, inverse square law means that force decreases with distance by more than by a inverse square. My bad. Okay, so this is what's happening. All right. So now we're gonna
Did you not?
correct our previous thing.
You didn't make that.
You ain't connected shit.
Okay. So inverse square law. Now people understand. Cool.
Yes.
Yes.
Yeah, there's.
This is
something
Actually
people
making
are
sense now.
Right. Okay. All
learning
right.
from the midterm.
So now we're gonna try to translate our distance into vector terms. How are we gonna translate that? We're gonna say that we're gonna replace d with the vector with the scalar r. What's the scalar r? The scalar r is just the it's just the measured distance physically between these 2 points. And to turn it into a vector, we're also gonna multiply it by the like vector r, which is the unit vector that's pointing between the 2 points to indicate direction, right? So you understand that this is just replaced, and this means direction. All right. So now we're gonna say that how do you represent our unit? How do we represent our normalized vector, right? We can calculate it by saying that our big R is defined by our R minus our point, right? So it's from R to R prime to R. Fuck this. Sorry. Yeah, no, I'm just very. Okay.
Yeah.
So go, my bad. So you're gonna take your R prime and R, right? And then you're gonna take your R prime minus R over here. So this is your vector up top, and you're dividing it by the length of the vector, and then the length of the vector is just represented by this by the absolute value here. So because you have 3 in total, you're just gonna write 3 over here. So now your Coulomb's law is gonna become this, all right? Cool. Is this too slow? Is this too fast? Am I going?
This is good.
No,
this
this is-
Am I talking about
Jesse, sorry, you missed a gigantic part of Coulomb's law.
Which part?
The Q1, Q2.
Yeah, the Q1, Q2 over 4 pi.
Did I not write that?
Not in the other thing.
Not in the other thing?
Yeah.
Not in that, not in
Not
that.
the
Oh
bottom.
no, because I just said that would replace that part. Oh.
That
Okay.
doesn't become the entirety of Coulomb's law, though.
No, it doesn't, but it becomes the
That part.
relevant part to what
This
we're
part.
talking about. It becomes the.
Yeah.
Your nickname?
All right. So
Jesse, sorry, how much longer do you think this is gonna go for?
I don't know. We started. When did we start?
Like an hour ago.
We
Yeah.
I
started.
don't know, I should check. the
Recording's
screen.
been on for 57 minutes and we
I
started
was
20 minutes
anticipating
in.
this to last around 2 hours.
Okay.
Okay, yeah,
Sounds good.
just asking because I
Early
need to.
calls.
Yeah.
Sure.
Yeah. I think I can go through most of the theory in 2 hours.
Okay.
Okay.
Because like this is the slow part where like we were not cover any of this vector calculus shit. They
Yeah.
didn't like
Yeah.
tell us why we're using the
Yeah.
amperage of the
This is
Gaussian
all
surface.
Yeah, this
It's,
is
like,
all.
conceptual.
Yeah, this is all very good.
This is really
Yeah, I
helpful.
feel like
Yeah.
tomorrow would be like a better time to do like actual
Like,
practice.
Yeah,
sessions.
yeah. Because
Yeah.
today
Today
everyone's
is all
going to
conceptual.
yeah. Also, I cannot calculate everything. I will die calculating.
Oh, I have one.
What are you looking for?
Sorry. Oh, it's in the
It's in the
closet.
Yeah,
Try.
please.
Because like you have like a whole
Yeah.
I'm not happy
Don't
to
take
get
it
it.
off.
Yes.
You just sleep.
Good. Keep
I'm
on
sorry,
sleeping
I'm
now.
not
Please
sleeping.
stay away.
Yeah,
Don't
don't
one. Please stay away. Just understand.
I feel like it's
I don't know, man, because I have to go through because I wanted to start with Maxwell's equations. And then I realized that it's impossible to explain that without explaining the physical meaning of it.
Yeah.
So then I started at the beginning of the course. I wanted to start it at the end of the course. I actually wanted to start at it.
Well, you've been kind of going back to it as a guide, so I think it makes sense.
Okay. Because I wanted to start at Maxwell's and then go to like EMAG waves that we covered in calc. but kind of stupid. All right.
Where's the beeping coming from?
Now we're
Sorry.
It's a
Tamagotchi.
My child needs my attention.
Oh, that's
So-
what that thing is.
I need
This
a-
is a classic
That's a
better.
medical thing. What's this?
Sorry.
It's yours? Okay,
Sorry, my bad. Oh, my bad.
that's fine.
Oh, I missed that part. Yeah,
Yeah,
indeed.
is this yours?
No.
Yeah, sorry, I just have to move this so I can get to here. Here, let's just. Can I put
Guys,
this-
are you gonna go now?
No.
Oh,
Can I
okay.
put this
I
here?
think he just needs to
Okay.
sleep.
Is that okay?
This guy
Is
is way too sleep deprived.
No, I'm just getting kind of.
Sleep well, son.
I'm not sleepy. I'm just sleepy for some reason.
Okay, sleep then.
Sleep well, either way.
Sleep well, son, and you can watch the recording
Get home
afterwards.
safe.
Get home safe.
Right, so
Son,
Yeah.
you want me to walk you though?
No, it's not.
You sure?
Is your home far
No,
from
it's
you?
not, but still.
all right,
Bye,
so
son.
Yeah.
See you
Get home
later.
safe. Text when you get home.
this is the classical experiment. Okay. So classical
Yes.
experiment, we derive a formula,
Nothing.
and then we find out that conceptually our understanding of what electric force should be, which is that it's proportional to the electric field, must also have been encompassed in our thing, right? So you realize that basically, if I were to write this as Q and Q prime, Q and Q prime, right? You realize that your E over here, that is just this portion without the charge of the test charge. Okay? So essentially we thought that we are trying to find something, right? And then we derived the formula from it by doing an experiment of force between 2 points and finding out the inverse square law. So now we're like, great, we have figured out how to define electric field in the classical space. So we are actually trying to define electric field in the wider context of the entire space, okay? And that's a bit problematic because now our electric field represented by force is very hard to measure now, right? So instead, we're gonna try to measure it from electric. So instead, we're trying to measure this. So essentially, what this course is about, right? All the electrostatic part is about measuring electric field flux, electric field by using the electric flux density, right? That is influenced by the material that you're using, and then over a certain volume. But then you did not measure force. So now you need to predict force. And then predict force. Applied to other objects. So when you say that there is a stronger electric field here, right? That is slightly greater than the electric field at the other point, you're saying that there is a potential difference between the two. So the potential difference is well, which way do you think it points, right? So you're going to the slightly higher one, right? So you're gonna say it's the potential difference is the amount of distance. It is the difference between the 2 points. So we're gonna say this is point B, this is point A. So VBA is equal to VB minus VA, right? And then because we're trying to, so basically what potential difference is a let's say snapshot of the underlying field after you have computed all of the relevant material information. You're going to store that information in the in the potential difference field, and then you're going to be like, I'm going to retrieve the point at B and the point at A, and I don't have to recalculate all of the electric field again. Okay, so that's why you use this specific version where you're like taking one minus the other. All right, so that's enough. So how do we measure electric field by using the electric flux density? We already talked about this, right? So the electric flux is when you take a volume integral of your electric flux density, which is, by the way, just Weber per density, I think. Okay, I think it's Weber
Yeah, Weber's
per meter cubed.
Oh, sorry.
So now we can say, okay, we can take in one of our Maxwell's equations and oh, sorry, it is per. My bad, I'm mixing up electric and magnetic. Okay, so this is that, and we're integrating it over. I'm so sorry. We're integrating it over a surface. My bad. So because of your and because we're integrating over a surface, we're gonna write this as a dot in the middle. So whenever you do vector integral, put a dot. And then because of our previously found out divergence theorem, right? So it means that this is
Your water
also equal to
Your water bottle.
Son, your water bottle.
is also equal to
You'll get it tomorrow.
the divergence out of your volume, okay? So the total amount of flux on your closed surface is equal to the divergence of the flux inside, which is, due to this law, also equal the volume charge density integrated over the entire volume, which is just the total charge, right? Can I understand? So this is called the Gauss's law.
I think I do understand.
So do you guys understand how to apply the Gauss's law?
I understand that.
You understand that? All right, cool.
Kind of.
So now we're going to move on to the magnetic version of this.
Can we go over one example?
I think, Jesse, I kind
It's the
of
first part of
understand
the
it,
course.
but a lot of people don't.
This is the first part of the course. Do you want me to go over this?
Yes.
Do you think it'll be important for them?
Not really.
Oh.
We can just jump straight into the magnetic field.
Maybe do
This is
one
sufficiently
example and
I
then go
would
to
like
the
that you do one example for.
All right, cool.
application's sake.
Yeah.
Why
You don't have to do the calculation, just like conceptually how
Really?
to apply it.
Okay, so I'm gonna say that I have a point at somewhere, and I'm gonna put a sphere around it. So the sphere is modeled by let me just see. I didn't even prepare for this part of the course because I thought we were done. All right, so we're gonna say that this is an example that I actually found. You have a spherical. You have what's it called? Concentric spherical shells, where there is some charge inside, right? Uniform, and the radius inside is A, the radius outside is B. And you say that because your electric field is in the shape of spheres, your electric field can be defined as some proportion of the radial unit vector, and then you say that your surface is closed, and therefore you write the Gauss's law. You're like, okay, my total charge inside is equal to the flux, which is equal to the integral of the d inside, right? And d is, because of proportionality, just something of E, right? Which is what we're trying to find. So now you say that because this is uniform all over, right? You're gonna take your E outside of your thing. So to take electric field outside integral, the important things that you need are that, one, it is perpendicular to surface at all points, for all points, x, y, and z. And second is that the magnitude must be constant across surface, right? So you're not actually affecting anything by taking it out of the integral. So therefore you do it. And you say that you have your epsilon e, let's just call this ER for convenience, and then for clarity, and then we be like differential surface. Differential surface, you just sub in the surface of sphere, which is like, I think it's like that, right? And then you have your, assuming you know the total charge that is inside, right? Let's just say 10 coulombs of charge inside. That's way too much. But we're gonna say that our 10 coulomb is equal to some quantity of ER times like 3/4 pi r cubed, right? And once you find this, sorry, surface area. Holy shit, my bad. Surface area. Thank you.
Wait,
It's 4 pi r.
Because then the 4 pi's cancel
Yeah.
out.
So 4 pi r. Okay, cool. So now you find this, and then you put this back into your original equation, and therefore you have your electric field. This is how you use the Gauss's law.
Okay.
Cool. All right, go for it.
Hi, just one question.
Yeah.
Actually, two questions.
Yeah.
Integral ds is just equal to 4 pi r squared because you're finding the surface area, and 4 pi r
Of
squared
sphere.
is a generally accepted equation for the surface area of a sphere.
Yeah.
Okay, second question, why did you write an upside down A?
For all. This is a mathematical symbol that means it just reads for all. So like, for instance, if you were to be solving Fourier series questions, it would be like n pi, right? And then and then you're like n for all n in like positive for all n in whole numbers. So
Okay, cool, thank you.
all right, so because this case is slightly complicated, that your sphere is like not infinitely large as your space, you're gonna have to define that slightly differently, right? Like you're gonna have to calculate that for different cases. You're gonna have to do one case for like your radius is less than A. You're gonna have to do another case for your radius is within A and B, right? So you would understand that when radius is like A, it's just 0 over here because no charge is inside the sphere. And then you would put your R as A, right? And here you would put your 10 coulomb, and then you would put like R as like some R, right? Like it might not be B or something, but this is just like how to use the Gauss's law. So similarly, we can define a Gauss's law, also called the Gauss's law, right? Using for the magnetic field. So we can check that our magnetic field has 0 divergence. What does that mean, right? It means that there aren't singular points that can induce magnetic field. It means that you can't find a magnetic so-called monopole, which is a point that acts as a pole, as in disseminating energy. So all magnetic fields must be caused by a positive N and a negative S, right? And N flows to S, so that's how it works. If I think that's correct, yeah.
Yeah, that's
So,
right.
how does magnetic fields align with electric fields? People have found that if you were to put, this is actually hard. Yeah. Do you guys understand how to use the
Right-hand rule?
yeah.
Yeah,
It's like
if the electric field is going up
Yeah.
north,
So if you have a current going that way, then according to
Right.
your
Right-hand rule is only for generators, right?
for all things. So your
Generators
electric
specifically
field,
want
right? Your electrons are happily moving along the wire, right? Which induces, which is the indication of there being an electric field, right? Because your charges are moving. So your electric field is also along the circle. And then when you do your what's it called? The right-hand rule, you just put your thumb against the electric field, and then your curl, right? Because your thumb is a point, the field with the divergence. This is the arrow with divergence, and then the rest of your hand, which is the arrow with curl, right? Because it curls. So this is the magnetic field, and then your palm is where the force is, right? Where the collective force is. So
it's going around.
yeah, in this case, you have your magnetic fields kind of like going that way. Oh my bad, I drew the current wrong. Okay, well, we can fix that by just inverting the magnet, I guess.
Yeah, I was looking at it very confused for several seconds.
Yeah, my
being
bad,
like,
my bad.
that doesn't work, or am I crazy?
So you understand that the magnetic field, right, is going like downward like that. This is the whole basis of electromotive forces. So I'll just go through how you go about solving an electromotive force problem, right? So let's say that I'm connecting my circuit up to a battery, right? And my circuit has positive over this side. And then I switch the circuit on, okay? I say, upon switching circuit on, is this too scattered? Is this just like a bunch of random concepts?
No, this makes sense.
Okay, because I'm doing it in a slightly different order than him because I thought that if I were to do it in this order, then when you look at his notes, you kind of intuitively understand. But it's not the most organized thing.
No,
So,
this is fine. This is great.
all right.
So what is electromotive force?
Right. So electromotive force is force that you can measure. It is a weird phenomenon where scientists figured out that whenever you turn this circuit on, the magnets align with the circuit, and whenever you put a magnet along your by different sides of your wire, the total electric field in the space is different, right? So if you put it on the right hand side of the wire versus if you put it on the left hand side of the wire, it will affect your current flow differently. So that's what people found, and that's what electromotive force is, right? So it's like the two things interacting with each other.
Oh, sorry. I have to discipline him. I'm sorry. No, he's asleep. I'm so sorry. I thought I turned off the sound. That was the highlight of my day.
Yeah. If we want to understand it from formulas, it means that the curl of the electric field, which refers to
Curl of the electric field, which
refers to current flow in a loop.
Yeah.
Right? Because it's curling.
Okay. Curl of electric.
Yeah, in loops. And then you have your is equal to the negative of the change in the magnetic field, right? So what does that mean? If I were to suddenly insert a magnet, this is a more intuitive example. All right. Let's say that my magnet originally was here, and then this is T equals like A, this is T equals B, okay? So my magnetic field changed, you see, because I put the magnet closer to the circuit. And my magnetic field generated by the magnet is going from north to south like that, okay? So originally, at time equals A, I had nothing. At time equals B, I had a magnetic field that was going downward, which can induce a current. And can you tell me which way is the current?
It's
Clockwise from our perspective.
clockwise.
Yeah.
Yeah.
Sorry, Jesse, one
So,
Is this the induced EMF we keep on talking about? Because I actually don't know what EMF is, but I just wrote it in my pre-lab.
Electromagnetic field.
So it's not electromotive force.
no, different.
Well, okay, different things.
Yeah, electromotive force is the thing that describes this law. Electromotive force is what the third Maxwell's equation is trying to describe. Okay?
Okay.
Electromagnetic wave, electromagnetic field, is just what is. Oh yeah. So altogether, these four altogether compose of the electromagnetic field. So this is a subset of the phenomenon of EMF.
Oh, okay.
Yeah.
Thank you.
So your induced EMF is going that way, right? So that's what happens when you put the magnet through the circuit, okay? But what is electromotive force? It's saying that in the opposite direction of how your magnetic field changed, which means that originally it had none, now it has more. So the amount that it changed was, sorry. Oh my god, I'm so sorry. Okay, so, no, shit, okay, my bad. This is very unintuitive as a concept because it's negative. So it's saying that, the charges in your circuit will separate themselves such that they will induce a collective current going that way, which opposes the one over here. So your material opposes, here, my bad. Material opposes change in the magnetic field, okay? So your material is trying to induce a current like this, which goes against what you think, which goes against how the circuit is. So this is a retarding force, which means that it makes your operation less efficient, right? And what the fuck am I talking about?
No, that makes sense.
Makes sense?
No,
Okay.
that does, yeah.
It's because the way I think of it is that, like, if your force created is not in opposition, then you would have infinite force for no reason once you started.
Oh, I see.
So that's how
fair.
I think of it personally.
That's fair. That makes sense.
It's just
Yeah,
right
that's fair. Yeah.
Yeah, it's like
So how you do EMF problems? If you ever ask to calculate EMF, right? Is that you will draw all of your situation, right? At t equals A versus t equals B, and then you would decide which either direction of current or which direction of magnetic field opposes respectively the magnetic field or the electric field, okay? So,
circular. And then material.
and then you will use your formula that is derived from your curl equation. But the curl equation is too hard to use, so we have an equation which is so EMF is equal to the delta. So this is the change of the magnetic field, right? Integrated over your surface. Which is also equal to your. So, like, I don't want to go into all of the like little details in here. Just tell me if there's something that you don't understand in this formula, because I cannot possibly talk about it.
Oh, stop it.
And importantly, it also means the
Okay, that makes sense.
EMF can be measured also by a force over a distance, which means that it's in the same unit as work, which means that it's also a measure of the potential difference. And then this is VL. So whatever. So this is the electromotive force equation that you need to know, and the unit for it is the same as voltage, is in voltage. Okay, so the part where we talked about the material opposing a change in the magnetic field, this is called the Lenz's law. And then the current thing that we're talking about is Faraday's law of induction. Okay, so I don't know if I need to go over the names of shit. That's awful. Okay, so here's a scenario that's
You probably should, just because there's going to be a conceptual question.
Yeah.
oh.
And, like, the first question is definitely going to be conceptual.
No, he said in the practice. Practice
Oh,
questions
okay.
he posted. The first one's gonna be conceptual.
Honestly, the exam would be so much easier if the whole thing was conceptual.
No, it wouldn't.
Actually, that was my lowest mark, that question.
Yeah.
No,
No, actually, no, that's not true.
No, it was my
That was
lowest
my
mark.
highest mark.
So here's a scenario where EMF we need to use, right? So let's say that I have a segment. Let's say I have a wire. I have a wire segment that's bent in a U shape, and then I put a bar over it. Okay, I put a metal bar over it that's connected to it. This makes a closed circuit, right? So the first thing that you need to check is that there is a closed loop, right? Loop is closed. Cool. And second, you need to check that you have, let's say that you have a magnetic field. So let's say that I define there being a magnetic field going, let's say, is this into or out of the page?
Out. I mean, in.
No, that's in.
That's in.
That's in. The one with the two dots is
The
out.
dot is out.
Okay, so this is gonna be my definition of the magnetic field, okay? And my electric field,
If there's an X, it means the current is going into the page, or the magnetic field is going into the page. If it's
I thought
a two,
X was.
I don't know.
X is going
Okay,
into the page.
we will define X as going into
Yeah.
the page.
It's because if you think of it like an arrowhead,
It's
the back of the arrow.
this one is out of the page.
Yeah. I think so.
Yeah.
And then if it comes out, it's just.
So that means the current is going around like this.
Okay, so yeah, you have a closed loop and you have a uniform magnetic field set up in your space, okay? And your magnetic field can, so what happens is that this magnetic field causes some current to flow through your circuit, and in order to oppose it, your material is going to separate the charges that it has inside. So when we learn about conductors, right? Conductors are these materials which, if you were to put in an external electric field, right? Let's say the external electric field is caused by a charge, right? Then your internal electric field will still remain zero. How? So the way it does it is by placing charges against your to generate a field that is opposed to your external field in the manner such as this. Okay, so this is your internal magnetic field. Okay, so your internal field opposes the charge that is being applied to it, and it's possible because conductor is a sea of electrons. Okay, that can flow. So in a similar manner, your bar will the charges in your conductive bar will separate. To oppose the induced current, okay? Well, actually, I think it's easiest if we just say that there's a current induced in the second step. So, that current induced. Okay, and then charge imposed to oppose it. Okay, that's chill. All right, so which way is the current?
It's going around this way, clockwise.
All right, clockwise.
So the currents created to induce it would be counterclockwise.
Wait, explain that.
Yeah, so this is the induced current. Okay, so when you mark this, when you do problems, be very careful. You call this the induced current from step 2. All right, so what's the current that you're trying to generate to oppose it? Which direction?
Coming out of the page from the left.
Well, the current.
Wait, is this the thing that's like electron flow versus current?
What?
I don't think so.
Okay.
Most of us don't know what that is.
Okay,
It's
so
like current.
They're opposites.
So
Yeah,
current would
so
be
it's going
going.
that way.
Yeah.
So if you have a current going clockwise.
Or, yeah.
I'm not sure if this is
Clockwise,
useful. I feel like I'm
they cancel each
wasting
other out.
people's time.
Why?
I thought you were asking about electron flow versus current. Never mind.
All right, so your current is flowing, like in the manner like this. Okay.
Yeah.
So, your charges will separate such that the internal field has currents flowing upward. Okay. So to generate that, all the positive charges inside of the bar, which I'm gonna draw over here, all the positive charges inside of the bar will come this way, and all the negative charges will come that way. To generate the electric field inside that is pointing upward. Okay,
Okay, sorry, Jesse, I have a question.
go for it.
So your current is going into the page, so your magnetic field is going that way. Therefore, since the induced current wants to oppose the magnetic field that you created, that's why it's going the other way.
The magnetic field is just applied by something else.
So is the X is like
The X is the magnetic field.
magnetic
Okay.
field.
X is going into the page, which induces a current to flow in the circuit.
Mhm.
But because there's a metal bar, which is a big reservoir of electrons, right? That big reservoir of electrons can oppose any sort of flow and give you stability, right? Relative stability. So they separate onto sides of the bar to oppose the external field. Now,
So if you have like your current going
yeah,
clockwise
okay.
here, then the thing that is going counterclockwise is only inside the conductor because that's where the field
yeah,
is
exactly,
going to oppose it.
yeah.
So the current,
Yeah.
that blue arrow has nothing to do with, well, not nothing, but like it won't have
Okay.
anything to do with the rest of
The charges.
Yes. All right. Okay, I need to run through this content now. Okay, so we have. What happens if we observe that when this magnetic field is applied, there is no measured current in the circuit? Then we say that the force that was induced by the magnetic field is plus the field. The force that's induced by the magnetic field plus the force that is caused by this charge separation must equal to 0. Okay. So in this case, something very interesting happens, which is that your electric field, which is defined by Q0, right? And then your magnetic field, which is defined by your Q of the move. Okay, we'll talk about this later. Is that okay? Too many things inside into each other. Okay. All right. So if we were to say that we understand that the magnetic field, we understand that's going in only one direction, we replace all this vector stuff, which indicates direction, to just like which direction it's going, right? So now I'm saying that my electric field, now I'm saying that my QVB plus QE, right, is equal to 0, which means that my E is equal to VB, okay? So what is this velocity? This velocity is the change in magnetic field. How do we induce a change in magnetic field? I guess I can like pull on the bar, right? So I'm gonna pull on the bar so that I'm gonna make the bar move at a certain velocity such that when it's moving at time equals, like, let's say x, right? I'll have more charges, sorry, more of these magnetic like field lines passing inside of my circuit, such I've increased the magnetic field. Is that okay? Is this bad? Shit.
No, I remember. This was a problem in the homework.
Yeah.
Yeah.
You guys understand? Cool. So now I've increased the amount of magnetic field inside, right?
Okay.
Which induces this pink current, and my charge further separates to oppose with the blue current happens here, okay? So this induced current thing only happens whenever the bar is moving. So if the bar is stationary, what's the pink current? 0, all right? So stationary magnetic fields don't create electromotive force.
Mhm.
So now you're like E is equal to B, right? VB. And then you figure out that your electromotive force is equal to the force EMF times the length, right? Times the distance that you moved it by. And then this is equal to your magnetic field per charge, right? So because your magnetic field is increasing. Okay, you guys will get this once we have a. This is just formula shit. Okay, formula is just magic. Okay, just use magic.
Just use them? Okay. Sounds good.
Yeah, only just use your thing. Yeah. So and then if you want to find the current is like the voltage over the resistance, and voltage. Guess what's in voltage? EMF. Yeah. So that's how you figure out the amount of current, and then because you use these formulas over here, right? This is the E is equal to VLB, right? So you just put VLB up top. The velocity, right? This is the speed at which you're pulling the bar. Length, L is the distance, like that you're pulling the bar for, and then the B is the magnitude of the magnetic field, and then R is the resistance of the system. All right, cool. So this is how we solve these kind of problems. We can do a homework problem here. I think that's suiting.
Sorry, Lissy, I'm lost.
Is that sensible?
I'm just lost. I equals V over R equals VLB over R. Where did LB come from?
V is a different V.
This
Is
is
velocity.
speed. This is potential
Oh,
difference.
okay, that makes sense. That makes sense. Okay, cool. And then V.
yeah, no, like this course is so hard to do in handwriting because like what is V, what is like this rel thing, what is like U.
Okay,
The
so
articles
difference equals velocity times length of or the distance moved, the bar,
Distance moved, yeah.
it
So, like,
times the
it's
magnetic
distance moved.
field. Am I right there?
Distance moved, right? So the magnetic field can be modeled by, let's say, like magnetic field coming out of the page. Let's just define that as like positive x. Okay, so we're gonna say that your magnetic field is equal to some amount of your x, which is coming out of the page. Okay, and you're gonna put Vx over here. Alternatively, you will put so Vx. You can put the just the true norm of your magnetic field. Is that cool?
Wait, sorry, can you play that again? I got distracted.
I moved and the couch squeaked and she couldn't hear. Can you say that again?
Oh, sorry. So alternative to like in the simple case, you can just put whatever the scalar is in your magnetic field. Okay. In the more complicated case, you're gonna have to take the true norm. Like the magnitude.
You need to find a unit vector of the direction of the magnetic field. Is that what you're saying?
No, you gotta find the magnitude of the magnetic field.
Oh, okay.
So the magnetic field, if it's only going in one direction, we only have to find,
Just take whatever it is, right?
and then any other case you find the magnitude of
Yeah,
it.
yeah.
I think my biggest issue is the unit vectors. I don't know why that's confusing to me, but
Okay, we'll talk about that later because I think
Okay.
most people should move slightly faster though. Because like we have some practice to get through. So I don't want all of this concept to take way too long. I'm already like, I took a bet on like going by first principles because I was like, is that gonna be any use at all to anyone?
When you say first principles, what do you mean?
Like, I was debating to myself whether I should have like started by talking about fucking like Gaussian surface shapes. Like, what is a compliance shape? You know?
No,
let's
no,
not
that's
just
good.
even that. You have to pretend like we haven't been to a lecture because we haven't.
Okay, alright.
I haven't mentally been at a lecture since day
Alright.
0.
Jesse, you flipped it upside down again.
It's good to me though. No, I don't want the cable on the right hand side. I have an iPad. It should be.
Yeah, I haven't like actually.
Like even when I was at the lectures,
Yeah.
I couldn't
Okay,
understand
so
what
this
he
is
was
the
saying.
homework.
Yeah.
Homework 8, problem 2.
We're
Alright.
at 8, damn guys.
And we skipped
So you take
4, 5, 6,
a-
and 7.
So similarly in this case,
That sounds like a
only
very
slightly
good
different,
thing.
right? In your circuit, there is not just a wire, there's also a resistor. And this has a defined resistance, and we assume the resistance of everything else is 0. So therefore, we have the VLB over R, right? We have our we have the R in this formula, all right? So magnetic field is going into the page, right? So
Sorry, Jesse, what does that say? VVB?
VLB.
VLB.
my
the
God, I will properly write things.
Okay. Is that equation just a given?
Yes.
Yes.
Just use it.
No, you should derive it from this whenever you need to use it. You write this whenever you need to use this equation, okay? You put this formula down so that he will be happy with you. If you put this formula down, he will be very happy with you. Just do that.
Okay.
So
Guys, bonus marks. Bonus marks. Bonus marks.
Hard marks.
That's true. I will take the part marks
Yeah.
where I can.
You're not
I
gonna
use
get a
like
part
marks
mark
as
for
possible.
realizing the equation.
I think he just
No,
kind
you
of goes with
totally
the
would.
flow. Like I feel like
You
just
totally
vibes.
would.
Like I
He
like
definitely
this
would,
answer. I'm gonna give it marks.
We never got the midterm back, did we?
No.
Did you go to the midterm to see what you did? Was Simmer you wanted to do it?
I wanted to, I asked him, he's like, you have to come see me during office hours.
Oh.
Yes, office
okay,
hours?
so
I really did not know about it until I asked him that.
so we're gonna assume that this is moving at some sort of velocity, right? And the distance of the bar is defined by length d. Alright. Oh my god, are you okay? The plushie is so cute though.
Me?
The plushie is so
I'm boiling. I'm very, very warm. And so I'm sitting on the floor to try and cool down.
Really?
Yeah.
Why don't you just sit like
Do you wanna sit by the window?
Yeah, you know.
Alright.
Because
It is not that much. I've sat there before. It's not that much colder there or there. And either way, it's still too warm.
Because the window's like right behind that.
I know.
Please go ahead.
Again, I've sat there.
Okay, then why don't you not down on the floor?
Do you
like,
want to
right
stand
here?
behind the couch?
No, I'm not gonna stand
Oh,
behind the couch.
that was mostly a joke.
Sit inside the fridge.
So part of this question, right,
I've done
asks
that before.
what would be if the bar is moving to the right with velocity v, what is the current in the resistor? Okay, in what direction does it flow? I think we can answer this question, cool?
Current in the resistor.
So first
Oh,
up, okay, first up, closed loop, we have a closed loop. Second step, what's the induced current by the magnetic field? Okay, so first- Think a little bit, right? Think a little bit harder. The bar is moving that way, so the magnetic field inside of the circle is increasing, okay? Instead of the rectangle is increasing with time. So therefore, because it's increasing and going into the page,
No, that's coming out of
It's
it.
coming out of the page.
sorry, okay, fine. Increasing and coming out of the page, right? So now what's the induced current of a magnetic field coming out of the page?
Counterclockwise.
Very
Right.
careful, very careful. Yeah. So it would be going this way.
Wait, how would you do
Uh,
that?
Wait, no,
Right hand rule.
And then opposite.
Right hand rule, okay? So
then
right
why is it
hand rule.
counterclockwise?
Wait,
No, no,
sorry.
induced current would be counter, but then the
this is
previous,
induced
like,
current. This is
the other
induced
current
current.
would be.
Alright.
It's just really.
Okay.
It's
What
just
the right hand
kind of
rule means
where
is
it's
that
opposite.
the
Is the opposite?
Only
magnetic field curls.
Oh,
This is
that's
your
the one where
fingers,
it's
okay?
going to induce an
And
opposite.
no, but
then
if it comes down, then it's going this way.
Like that's
This,
the current
uh,
outside
this
resistance,
is going
but the
counterclockwise.
actual field
and
inside the
this
conductor
is
is
your
really opposite.
Yeah, I understand that, but
Oh, okay.
it's still going this
and
way.
palm
Oh, yeah.
is your
Yeah.
force. Okay, is that cool?
Sure.
Actually, yo, this is cool. EMF. This is the direction of EMF. Cool. All right. So
Oh, okay, yeah, that makes sense.
make sense? All right.
Yeah. This like the right
This is how to use the right hand rule. All right. So we figure out that the induced current, right, by the magnetic field is in the purple. Is in the pink, and then now therefore we have the current that is going in opposition to that,
the opposing.
and therefore
current
to
is-
oppose it, right, our charges are going to separate into this. Cool.
And then, sorry, Jesse, I think you already said this, but I just want to make sure.
Yeah.
The opposing current is only in that little thingy, the metal thingy, right?
Yeah.
Only.
Mhm.
Not anywhere. Okay, that makes sense. Okay,
Wait, sorry, how? Those are two different planes.
cool. No, it's because
Hmm?
you have the current in the wire, but then the big
Oh.
the metal is on top of the wire.
Sorry. Jesse,
Hold on. No, I'm not getting the geometry of this.
Jesse, sorry. When you say it's opposing the current, the charges, current is the movement of positive charges. So wouldn't it be, if to oppose it, wouldn't the pluses be at the bottom?
No.
Wait, let me
No,
check.
because
Let me
current is the movement of negative
No,
charges.
it's
Sorry.
positive.
No, it's not.
Electron flow is negative charges.
Isn't current electron flow?
No, it's
Current
is the
opposite.
inverse.
They thought that positive charges moved back then, so then they made like a bunch of
Everything.
equations surrounding around that, and then they realized it was electrons that actually moved. So their electron flow is the opposite of current flow.
Sorry, I
It's really dumb.
don't
Benjamin
understand.
Franklin fucked up.
Fuck that guy, man.
I don't
No,
All my
understand
homies hate
how
That's
we
part of
get.
it.
That's the thing, is that people always just think they have to type
Purple
and they go
current.
back to like
Yeah.
change graphs or whatever, or
Purple
like
current?
fix things.
Your
Like
magnetic
literally
field's
just
coming out
the
of the page,
equations and
your
shit.
fingers are going
Oh, like I go back to Benjamin Franklin.
Yes.
No, we're doing it wrong. Switch it around.
Yes.
Conventional dealt with current flows from negative to
My
positive.
bad.
Okay.
This is,
And then you'd probably be
But
like,
then
you're an idiot. I'm
that
sorry.
isn't.
Actually,
You'd be like, you're a woman. How do you know this shit? Are you a fucking witch?
Yes.
That's how it would go.
Yeah, probably.
That.
it would really help
The
because
blue one?
like
Yes.
That's
you're
the
not
charges
so he
that are
probably
Well,
needs
you
to
could-
be
you could
like
like-
more.
in
Wait,
a.
guys, I'm
wait,
teaching this
this-
wrong.
Yeah.
But I mean, other than
No.
Guys,
like-
I'm hopelessly teaching this very wrong.
Why?
Yeah.
Why?
What's the wrong part?
What's wrong about it?
The wrong part is I'm not using the correct examples. And that I
Okay.
am using the wrong order.
Are you okay?
Yes, my phone fell when I did that.
Okay.
Then I got it.
Shit, I feel like I'm
Okay.
failing at this. I'm gonna make all of you guys fail.
I'm like,
Shit.
You can't make
You're gonna
me
fail
fail.
before, so like, this is step up because at least he'll look at
I
it.
can
and
write
like,
something.
Yeah,
Yeah.
he'll at least
You
look at it
will
like you
single-handedly
tried.
be responsible for all of us getting at the very least 50%.
That's optimistic.
Besides, if we fail, it was our own fault anyway for not
Yeah,
like,
exactly.
getting our shit together
Yeah.
earlier. But
Yeah.
if you pass, it is
Absolutely
you.
Jesse's.
So
But
like,
at the same time, we shouldn't have to teach ourselves.
yeah, that is true. I literally was too busy teaching myself calc. I could not
Okay,
figure out
okay.
the rest of it.
Yeah, actually, that's that.
But Jesse, also don't take it upon yourself. Like whatever happens.
Yeah.
It's like,
Oh,
no,
yeah,
do it all.
exactly.
You're doing nothing but helping us.
Yeah.
Yeah,
There is only positive outcomes.
There is, yes, exactly. Matt, you know
That's
what's
not
up.
true.
What?
With
So-
your support, we can make the reading.
I was the first you.
Okay.
Okay, actually, this is fine. I just freaked out a bit. I'm sorry.
It's all good, Jesse.
I know how
So
we
first,
can do
identify
Yeah,
directions
you're
of
a
induced
little-
current, and identify direction of the currents generated by the bar, which opposes it. And the current generated by the bar, right? It creates sort of a, let's say, friction version in circuits, right? So it makes this speed actually goes. It wants to make the speed actually slower. So we call this, let's say, the force of like, let's say the induced by
It
the
works the other way too.
by the
Would you mind like
Power?
labeling some of the variables just
Yeah, this
Uh,
is north,
for memory
and then this
issues?
would be current, or this is current.
maybe take notes.
Yeah.
Yeah, take notes then.
I think that would help.
Yeah,
So
take notes.
Oh, you can
magnetic
look at
field by the
Yeah.
opposite induced current is
Can you explain the palm thing one more time? The palm? Because
speed
I know you
is
used the direction,
perpendicular.
but like.
We haven't run into
Speed is
a problem which we need to
perpendicular
use the
or
palm
speed
yet.
perpendicular.
Just
Oh,
leave it
okay.
at all.
Jesse, are you gonna eat that entire guacamole?
Oh no, man.
Maybe
Okay,
we should remove that from you.
She
whatever.
deserves it. She deserves it.
Okay.
Wait. So the bar moving is caused by the electromotive force.
No, the bar moving is someone moving it.
Oh. And that causes the the
Everything that I write in gray is things that are set up for the system.
okay.
Something is applying magnetic force.
So magnetic force is being applied like this, and current is going that way. Current then applied by the magnetic force is generating a magnetic field that is going into the page. So speed is perpendicular to all of this. Does that not affect anything?
Constant speed, force is 0.
Huh,
Newtons, remember?
yeah.
Newton's laws.
Yeah. Or we can write it as the force, right? Like classically, you write this as mf. Sorry, F equals like ma, right? And then you write the force is equal to the. Oh, and then sorry, yeah, and then the A is equal to the dV over dt. All right. So the whole thing you can write as your force of your magnetic force. The force induced by your opposing charge of the force induced by your separation of charges is equal to the mass times the dV over dt. All right, and then the dV. How do we calculate the dV? Wait, what am I doing?
This is a first order separable differential equation.
Fuck you. Eat shit.
None of them just divide the D's.
Guys,
Cross out
The D's cancel out.
is it too late to transfer now?
Yes.
No, it's never too late.
It's not.
You just might have to redo all your years.
I might have to wait. I submit my application. Oh, you did?
So this is the one formula that you need to have in your formula sheet about EMF and these like
I'll tell
bar
you
situations, right? You have to write that your thing is equal to your to your blue I, right? D blue L, crossed by magnetic field originally. Okay, so this is the one thing that you need to know about this to solve these problems, right? And now you decide that your current, right, is going. Your current is going downward. Wait, sorry. Okay, I did not define. Okay, you need to write a coordinate axis, which I was bad at. So I'm gonna say this is Z and this is Y. Is that okay?
Yeah. What's A and B?
A and B.
They're
Yeah,
just
on your
The
integral.
bounds
points.
on the integral.
This
it just
is
any
the 2
2
points at the 2 ends of the bar.
Okay.
Okay, so like A and B would be separated by D in the middle, right? So you would integrate from 0 to D.
Right.
and D is the length of the
Yeah, and actually this should be
Cancel out,
opposite.
right?
obviously. This is like math 117 stuff.
Okay. So oh shit! I wrote them down wrong again. Oh my goodness.
I'll help you, Oscar.
All right, so you're integrating from 0 to D, right? In terms of your z-axis, right? And then what do you put for I? For I, you define. So basically, you just have to find some sort of explanation, right, to put your line integral to use. So I'm integrating over the bar, right? So I say that the I is pointing downward during this part of the thing. So I'm gonna say my DL will become DZZ. Is that okay?
What?
So DL has
Oh, this is the line.
the line
vector thing.
integral
Yeah.
has a length and it has a direction. So I'm just separating the line from the direction. Is that okay?
Yeah.
Yeah, cool. And Z is because it points in the Z direction. Yeah. So, and then I'm gonna say that I have my magnetic field. My magnetic field is coming out of the page, right? So I'm just gonna say that my x-axis goes that way. So I'm gonna define that as B with x, okay? And then z times x, do you know how to do vector cross product? Okay, so the way you do it is by writing all of your vectors that are all of your vectors are perpendicular to each other in a certain order. So in the current order, this is actually in our configuration. Holy shit. Okay.
What?
What? It's in the clockwise configuration. there is a specific
Jesse,
angle
I
at
don't
which
know.
you can hold a cube.
Jesse, I know how to calculate cross product. I have no idea what the fuck you're talking about.
Okay, so usually you travel clockwise, okay? Clockwise the correct direction.
Jesse,
So,
what the fuck?
If you were to number 1, 2, then you arrive at 3, so that means x crossed by y is equal to z, okay?
What?
If you were to happen to travel in the counterclocks, so
Yeah.
this is because it's clockwise. So if you want to calculate the cross product of z times x,
This is right-hand rule, right?
then you just say that, okay, how do I go from z to x? This is also clockwise. So clockwise means positive, okay? So I'm gonna put positive y over here.
What?
Wait, wait,
Oh.
Right-hand rule,
You're going
right-hand
to
rule.
X.
It's a wraparound buffer.
I thought you were going from Z to X. Wouldn't you go counterclockwise?
So, no,
This
okay.
thing is
okay.
a circle. I'm sorry.
So,
This is bad.
Jesse, can I?
Go for
Cross product, it's a thing that we did briefly in both 117 and 119, and maybe when you're algebra, I don't remember. Cross product is a way to relate directions of two vectors to a third vector that is orthogonal to both of them.
Oh,
So-
orthogonal.
Okay.
90
Orthogonal
degrees.
is 90-degree angle, but it's in
Oh, you
three
guys don't even
dimensions.
understand the definition.
Oh, wait,
Okay, I thought that
So yeah,
It's been a
But
while.
if
We
it's
need
like
to remind
if
us.
it's like
Alright.
X and Y, then the orthogonal one is gonna be Z.
Yes,
Yes.
because so yeah, X, Y, and Z are in
But
like
it's-
cube.
Yeah.
It's
Okay.
It's a third plane.
Yeah,
Okay.
and so for this cross product, or not cross product, right hand rule, X going on to Y going on to Z is like this, but then Y going on to X going on to Z is like this, so it's negative Z.
If you want to know one thing about cross product, is that this operation is anti-symmetric.
Yeah.
What that means is that if you were to do, it means that the commutative property doesn't work. You want, usually when you times x by y, you want it to also be y times x, but because anti-symmetry is actually the negative of the y equals x, which means that if you were to time a thing by itself, well, you copy the same thing down, but it also has to be equal to the negative of the thing, right? So it means that all of these is just 0. So this is why when you cross something by itself, it's 0. Because it needs to equal the opposite of that. And similarly, this is why when you define x and y, right, is equal to z, then when you do y cross x, you will get negative z, all right? And this, if you were to think about in a very simple way, is if you write x, y, z in the order that you want to be positive, and then you decide that the counterclockwise order is positive, then you will just cross by deciding if it's clockwise, positive, counterclockwise, negative, all right? So you'll be able to simplify your cross thing to y, right? And because again, I is constant at all points inside of the bar, and it is also either perpendicular or parallel to the bar, which it is parallel to the bar, and therefore you can take it outside of the integral, and then you, same with the magnetic field, is perpendicular to the bar, right? So it's also uniformed. You take them all outside of the field and you integrate 0 to d on the z-axis, which is just distance of d. All right. So this is how you simplify things. Chill.
This is so much simpler than anything he's done in class.
So
Sorry.
I
This,
can't.
this makes sense. That said, I feel like we're going to run into trouble using d both for distance and for derivative. Yes,
that's what he uses.
I know it's
I
what
will
he
write
uses.
all
And
my
can you
d.
use? Could you use partial for the like the
Yeah,
partial
that's
is
what I was
like a
about to
backwards
say,
sense.
because,
Yeah,
like,
thank you.
I am fine doing that. It's just like okay.
Thank you.
Or use big D for the range, which is wrong, but like.
It's more
Alright.
wrong than partial.
No more corrections.
thank
No more
you.
corrections. I'm done.
Thank you.
I'm done correcting. Is that okay?
Yeah.
It's beautiful.
Yeah, that's
So-
only
Hey
where
guys,
you need to go.
no, yes, but also, or actually, I just, there's someone who just, never mind, they did texted like 40 minutes ago. We can't write solutions to problems.
But can we write steps to problems?
No.
Only equations.
Oh. He already clarified this.
Wait,
yeah,
why
why
do
did
the
we-
definitions though, does it?
Huh?
Why did you not just?
We're never
use
gonna
the
finish.
sheet?
Jesse, how long do you
So
think we'll be
probably-
until we finish up this?
I don't know, mine keeps getting interrupted. It was gonna be like 2 hours, and then now we're like an hour and a half through. I don't know.
Yeah, so
We
you
took a
can,
break.
we can have like titles to equations. And
It's
stuff.
been exactly 2 hours since we started streaming.
Yeah, because like just constant interruptions. I don't know how long it's gonna take. It's gonna take forever.
I think I should probably go home like now.
Go, yeah, go instead of like being anxious about going.
Yeah. We take a little break. Little break. Is that okay?
Yeah,
Well, whoever wants to go on for a
Probably.
walk
have a break.
with me to my car,
Where's your car?
It's in the car.
It's right there.
it's away. It's dark and I don't want to walk alone.
Okay.
So,
I need to stretch my legs.
yeah, whoever wants to stretch their legs, you're with me.
I'll do
I
it.
think turns out that I have to teach not only electromag, but also the whole of like vector calc and linear algebra.
Yes.
That's what happens when you have a nearboard G.
Yeah.
I mean,
Also,
to be
guys,
fair, I haven't used any of these skills since a year ago.
I don't think we need to focus on vector stuff.
We kind of do.
No,
unfortunately.
not, I meant like as a group, because it does seem like a waste of time if we can go over it by ourselves.
Yeah.
Just because we've already technically learned all of this, so it would,
Exactly.
it would.
Jesse,
Yeah,
what is
but
your
at the same
plan
time, like,
for
it
what
would
you
waste
want to
us
get through
time,
today?
So,
I wanted to get through EMF. I wanted to get through electromagnetic waves, like plane waves. And then I wanted to get through the derivation of the integral forms of Maxwell's equations, which I did half of it. And then I wanted to go through the application of M-prime.
unfortunately, we're dumb.
Yeah, I think we can try for a bit more, but it all depends on like.
Well, I'm
It's
done.
really frustrating.
Mhm.
I think
Whenever
I think
you're done,
tomorrow-
we'll just leave.
I think tomorrow I need you guys to all review like how to take an integral, okay? Like how to take an integral, how to take a line integral, how to describe a sphere, okay? And then we're gonna start tomorrow with M-prime loops, finding magnetic fields, right? And then dealing with a cylindrical object and finding everything about the solenoid.
Okay,
Can you tell us which lectures this is so we can just like read through it maybe to get a basis? So we're not prepared.
also, when are we starting tomorrow?
tomorrow?
When do you guys want to start?
Your choice. You're the one like doing everything, so
Yeah.
you can choose.
And it's gonna be here, right?
Is it gonna be here or is it gonna be on
Campus.
campus?
I'm under the impression that I'm wasting half of you guys' time because this is the same problem that profs have when they have a group of students who have a large skill differential. For instance, like Sam left because he thought like it was going too slow. So I think that like I'm either I want some proper feedback on this. I don't know what I'm teaching. I don't know what's-
Understandably, San is the exception out of the people here.
Because
Yeah, Jesse.
Because he's
No,
Your
There's
Proper
not a big
feedback.
range.
none of the, like, with the exception of Amanda,
Mm.
none of us know anything.
And in all honesty, we feel more like we're wasting your time.
yeah, if anything. So like
It is actually really hard to go at a slow pace
Yeah.
because like I have no clue what I'm gonna be able to get through. We don't have that much time before the final, so
We don't.
I'm just gonna force you guys to go on my pace if that's okay.
yeah, that's fine.
Yeah, it's fine.
Can you just
Also, to be pessimistic or like optimistic, on the midterm, it took me literally doing a question and a half to beat the curve. Like, we don't actually need to finish learning all the concepts.
That's-
We need to get through enough of it that we can figure the rest out.
I don't. That is true, however, that is an individual decision rather than a group decision.
I know, I'm not making the decision, I'm just like,
Also, it's only useful to me if I finish teaching the whole course content.
yeah.
What should we look over for tomorrow? Like maybe like assigned reading basically.
There's nothing that you can look through very much to help.
Do you think we could like look over the lab material? I feel like that really helped me learn a lot of this stuff.
Sure, yeah. Look
I think
over
that's
that, look over like
Yeah, somehow the lab.
Yeah.
search up how to calculate a line integral. Search up how to calculate surface integral and the volume integral.
I think, the other thing with this course is the biggest issue is that there was hardly any external resources that matched up with the level of our course. Everything was either too simple or too overcomplicated. So there's no
Like, I
real
can't
readings
follow
to go through other than the
that.
textbook, and that's
Yeah, no.
wasn't set up very
Okay.
well.
I think the best introduction to this would either be that everyone has a printed out formula sheet. So I can just be like, I'm not gonna explain this, but go check out line 23. Okay? Another option that we have is if all of you guys understand how to calculate things. I think part of this course is setting up things, and the second part of this course is calculating things. If I can go through questions very fast by only going through the part of how you set it up and not have to go through the calculation, then it will go way faster. Okay, so that's the option 2. What do you guys want?
If that's it, we should probably.
Like, I can go through almost all of the homework problems, but it wouldn't have any calculation involved. It would just be like, from this formula, because we set these up, right, and then we substitute in this other value, which we've set up to point towards x direction, then you will get this. And then you use that to do the next thing. So I will only go through steps, and then that's another option.
I think
that will be
I think that's
useful.
useful for me personally. I don't know about what other people think.
I think that'll be
I
useful
think
for me.
that I probably I'm just talking for me personally. I feel like I need to go home and review this stuff then, so then we're not sitting here until 10 wasting
Time.
Yeah.
Because
Yeah, so maybe concepts, go through it. But concepts is the hard part to understand, right?
Oh, for me it was the opposite. I'm shit at the math part. But I don't know.
Yeah.
Okay, I'll just go through 10 types of problems tomorrow.
Okay.
And then I'll have the formulas organized in which questions will use which formulas. And then all the unused formulas I'll put on a different part of the page. Is that okay?
That sounds good.
That's good. Because then we can go through the formulas and see what we need.
Yeah, and I'm assuming those are the most important ones anyways.
And that's kind of gonna be our format of our exam, and then we can go home on Sunday, let's say, do
Just go
review
calculate.
and just calculate. So then we'll know how to set it up. It'll be like
Yeah, that's a
How
good
we
idea.
organize it.
Yeah. Okay.
Okay.
How long is
Hardest
that gonna
part is setting
take
it up
us?
for me.
setting it up. So then setting it up.
Stop interrupting, and it will take maybe 4 hours.
Okay,
10
then
questions, 4 hours.
Well, the interruptions we're not interrupting for the sake of it. The
Yeah,
interruptions
no, I
are for the sake
understand.
of,
Yeah.
Comprehension.
yeah, so if you don't interrupt, we'll technically get through
Like-
4 hours of content,
We
but we'll
won't-
still be stuck
We
on
won't
1 hour.
understand
thing.
anything.
okay, I think we should schedule 2 hours for interruptions, so that takes us to 6 hours.
Or wait, why don't we
Just judging
frame this?
based on what happened tonight.
Okay, I have an idea.
Do you want me to be a whip?
Okay, can I just say my idea?
Yes.
Shut up. So here's how it works in classrooms. The teacher teaches their lecture. You save all questions until the end of the lecture. We can do that. That way, if you have any questions, you write it down, and then when she's at the end of it, she'll be like, "Do you have any questions?" Then you can ask them, and it'll go by much faster instead of interrupting her at each step.
But also, I was
That
being.
That
works for
That works for a
calculation
lecture where
stuff,
content-
but
That works for a lecture where content is sectioned into 20 or
So
so
that works
lessons.
for stuff like chemistry, but for calculus or this, where each step is important, if you don't understand one step, then making it to the end of the lecture won't matter. So that's why the interruptions
Well,
are there.
Okay, so I have another
calculation
proposal. I have another
so
proposal.
that's
Okay.
not the case.
Yeah.
So,
But it's still.
is there
it's
anyone who
flexible.
was able to follow my case?
This was your
Okay.
pace?
Yeah.
Okay, yeah, I was following fine.
Yeah.
Okay.
Yeah, this
So
is fine.
This is fine.
This is a great
It's
pace.
just
Okay,
the
this
interruptions.
is a great
slightly
pace.
more. Okay, so if someone can follow at this pace, then that someone will be in charge of explaining it to everyone else at a more granular level. Is that okay?
Okay.
Yeah, like we all
I think
help each
that would
other,
be-
like group study
Yeah.
basically. That's
Yeah.
fine.
Okay,
When you
so
say-
you
when you
keep
say your
talking
pace,
and
Do
then
you mean what actually happened or what you intended to happen?
What I intended.
Okay, then I don't think anyone here could follow at your pace. When they say they could follow at your pace, they mean like they could follow along with the pace that we were actually.
Yeah, I don't have a basis for what your intended pace
Yeah.
would be.
Did you mean like this question specifically, or do you mean like overall?
Overall, I wanted to go like about twice as fast. But also like I made a lot of mistakes on the way, so that was part of my fault. So for
Okay, I
tomorrow, I'm gonna make sure I don't make as many mistakes, and then we're gonna kind of structure it in the sense that like you'll all attempt the problem as I'm going through it. Is that okay?
no, I think
That's
what
what
you
you do.
said before would be a good idea. Like I know a few of us, like I kind of got it, Nat kind of got it, Oscar kind of got it,
Okay.
and then we can kind of answer
This is
questions
so-
among ourselves while you go at the pace that you want to go at.
So I think that
And if we have
Someone
frequent
was-
breaks, this would work too. Like
Yeah, how about like every hour we have
break, and then we can
15
discuss with
minutes
that.
and we can discuss,
all right, sure.
because like
Yeah.
your pace is
I
great.
can do that,
but-
or I can just like not
yeah.
host this.
I was also curious what resources you were using outside of his lectures to understand all of this because I was.
Nothing.
Oh, so you just understand him. Okay, that
I just
was
figured
my
it
big sister. I literally couldn't find any other resources that
Yeah.
like explained it to a decent level of complication.
I don't know, bro. I heard the chat.
Okay, we figured out what we're doing tomorrow.
So when are we starting?
When are we starting?
Jesse, your turn.
Let's say that we start at
1 hour before we actually.
12.
12?
So 11.
So 11. Be here for 11.
Here or on campus? Let's decide that right now as well.
Jesse?
Okay,
let's
we
do it on
actually have to-
campus because I think my roommates will be annoying.
Okay.
PWE?
Yeah.
PWE? Or-
Wait, let's check if there's any.
I can't.
Yeah.
What do you
mean
mean?
you can?
Look at the
We
overall
can.
event schedule.
They don't have dates, they don't have locations listed. I tried.
We're literally looking at it.
Yeah.
Like we
Like,
were.
I
Just
checked-
search a few Waterloo
I checked
exam
3
fall
days
schedule.
ago, and it didn't have classrooms listed.
Oh, it does. It
Yeah.
does. We checked like multiple
Okay, well,
times.
when
I
you
think
figure out the
UW
classrooms, let me know. I'm going home.
Okay.
Yeah,
Should we
so
walk
we'll
in?
meet up
Yes.
at 12. Try to be there around 11:45.
Actually, I'm gonna go to the bathroom.
I'm gonna try to wake up such that I will reach there by
Oh, yeah.
11:30, and therefore I need to make the set of questions and go through it. Actually, no, we can't start at 11. That's too early. Not enough time. I'm gonna have to go through it myself first because I don't want to do it very slowly, and I don't want to make mistakes. So we're gonna do maybe 1 p.m.
1 p.m. Okay.
Okay.
That gives us enough time to do grocery shopping.
Be
1
there,
p.m. and then
be there early. Like 1 p.m.
12:30.
if we can all.
Yeah, 12:30, and then we'll actually like be in the class at 12:30, and then we can start this. So like the stream set up, get everything.
That's a good idea.
If the class is busy, we could actually just use my place.
It's a little too small for, what, 8 people?
It's the same size as this, and I have pictures.
Do you have a projector or
Is
is
it
it?
I have a
TV?
TV
Okay.
that's bigger than this. a bit.
We should ask. Is anyone watching the stream?
we might have more people tomorrow.
Yeah, we are.
I genuinely have no idea.
I don't
No,
think so.
at this point, no one is.
No one is what, sorry?
Watching the
Watching
stream.
the stream.
Time